Okay, so part three. Let G be a group of this order. This 126 equals 2 times 3 squared times 7. Part A, determine all possible values of the number n7 of silo 7 subgroups. Okay, so this n sub 7 here, rather, of silo 7 subgroups. So it's a silo theory problem. And by Silo's theorems, we get the following for n sub 7. And then this is just going to be 126 over 7 is 18. Divisors of 18 are 1, 2, 3, 6, 9, and 18. And among these, the only one congruent to 1 mod 7 is 1. So n sub 7 is 1. Part B, determine all possible values of n sub 9. So a Silo's 3 subgroup has order 3 squared equals 9. And by Silo's theorems, we get the following. That equals 14, so the divisors of 14 are 1, 2, 7, 14. And among these, the ones congruent to 1 mod 3 are 1, 7. So thus, n sub g element in 1, 7. Part C, show that every group of order 126 has normal Silo subgroup. Since this n sub 7 equals 1, there's exactly one Silo 7 subgroup. Unique Silo subgroup is normal because conjugates of a Silo subgroup are also Silo subgroups. And since there's only one, every conjugate must equal itself. Therefore, every subgroup order 126 has a normal Silo subgroup. And part D, determine which Silo subgroup must be normal. The Silo 7 subgroup is normal. Okay, moving along to number 12. Okay, so number 12, fundamental isomorphism problems. Here are they, here for A, B, C, and D. Fundamental isomorphism problems. So if we define the following here, for that Z, adjoint of X, Z by evaluation at 0. If we're going to do this part A here, this phi of that f of x equals f of 0. This is a ring homomorphism. It is surjective because every n is in Z, is the image of the constant polynomial n. The kernel consists of all polynomials with constant term 0, which are exactly the multiples of x in this kernel here, psi equals of x, but phi rather. Did I write that as a, I'm sorry, that's a phi. I should have, okay, never mind. By the first isomorphism theorem, we get the following. Okay, so I wrote kernel of phi, sorry. Part B, we have a psi, sorry, that's psi, define psi for the following here, that all real numbers adjoin complex. So by this following psi of f of x equals f of I, this is a ring homomorphism. It is surjective because every complex number has this form, a plus bi, and here we have this a plus bx, and a plus bi, and the kernel consists of all real polynomials vanishing at I. So the minimal polynomial of I over all real numbers is x squared plus 1. Therefore, we get the following for that kernel psi. And by the first isomorphism theorem, we get what we were trying to show. Just condensing the verbiage. Part C, we want to show the following. So the norm of 1 plus I is n of 1 plus I equals 1 squared plus 1 squared equals 2. And if that Z adjoint I, the quotient by the principal ideal generated by a Gaussian integer of norm 2 has 2 elements. Okay. Alternatively, since 1 plus I equals 0 in the quotient, we have I equals negative 1. So also 1 plus I times 1 plus I equals 2. And since 1 plus I equals 0 in the quotient, this implies 2 equals 0. So every class reduces to either 0 or 1. And so the quotient has exactly 2 elements. And for part D, identify the resulting quotient ring. In this field, there's only one field with 2 elements for that F2, so we get the following. Okay, And that's number 12. And moving along to the last one, number 13. Let me just take this down here. Number 13. So we have an abelian. I'm sorry. We have a abelian problem. So let G be a finite group such that every non-identity element has order 2. Part A showed that G is abelian. So we take arbitrary A, B in G, and if A equals E or B equals C, B equals E, then AB equals AB equals BA immediate. Assume A, B cannot equal E. Since every non-identity element has order 2, A squared equals E, B squared equals E. Also, if AB does not equal E, then that quantity AB squared equals E. So AB equals E, BAB equals A, BA equals AB. So A and B commute, thus G is abelian. Show the following. This isomorphism for the integer n is greater than or equal to 0. For part B, since every non-identity element has order 2, the group behaves like a vector space over F2. We define that scalar multiplication by 0 times G equals E. And G is abelian, and we write the group operation additively, and every element satisfies G plus G equals 0. Okay, so G is a vector space over F2, and since G is finite, it has some finite dimension n. So we get that isomorphism, and as a group, we get that F sub 2 to the n isomorphic to Z2 to the n, so that G is isomorphic to that Z2 to the n for some n is greater than or equal to 0. And for part C, determine all possible group orders that can occur. So since that G is isomorphic to that Z sub 2n or Z2n, the order of G equals 2 to the n. And therefore the possible group orders are exactly 1, 2, 4, 8, and 16. Okay, so or equivalently there at the bottom that given the order of G equals 2 to the n for some n is greater than or equal to 0. Okay, so that's all for the practice problems, and thank you very much and have a great day.